Is it working? Okay, thanks.
You want to start?
Yeah, okay. So basically, I'm Junfeng Qiao from Professor Nicola Mazzari's group at EPFL. So today I'm going to talk about automated Wannierization, that is to obtain Wannier functions automatically. So as Professor Nicola Mazzari has shown us on Monday, the maximum localized Wannier function are just mathematical transformations of the block wave function. So there are two transformations. The first one is this unitary transformation, which mix block states of different bands, and then the Fourier transform, which brings this reciprocal space to the real space, so we can get these localized objects, like these S and P-like Wannier functions for the valence plus conduction bands, or the bonding and anti-bonding Wannier functions for the valence and the conduction, respectively. So how do we obtain the Wannier function? So first, since they are maximally localized, so we first need to define a measure to estimate the localization. So that is why we introduce a spread functional. So the spread functional is defined by the square of the position operator minus the square of the Wannier centers. So this is just the variance of the real space orbital. So noted that the Wannier function lives in this nk cube supercell. So if we do this naively in real space, this will incur a large computational cost. So this is why we need to do a k-space discretization. So we introduce these B vectors to approximate the derivative of the function. So these are the B vector just for finite difference. Then we can rewrite the spread functional as some mathematical transformation of these M matrix, which are just the overlap matrices between different block states at different k points. Then our second objective is to minimize the spread functional. To do this, we need to compute the gradient. So I'm not showing you here the formula for the gradient, but essentially it's just algebra. Once we have this gradient, we can pass this to an iterative algorithm, and then the minimizer will give us the maximum localized Wannier function. So specifically here, we're minimizing the spread functional on a matrix manifold if you're mathematically oriented. So this is a matrix manifold of unitary matrices. So it's a constraint minimization. So in fact, because the Wannier function and the block functions are just Fourier transform pairs, so naturally we have this real space localization, which is correspond to the k-space smoothness. So imagine like for signal processing, the k-space here is equivalent to a time domain, while the real space is actually the frequency domain. So if the signal is like smooth, then we will have a lower bandwidth in the frequency domain. So that is why we often want to have maximum localized Wannier function to get the most compact signal. So what we need from the spread definition is that the M matrix, which is written to the MMN file, and then another A matrix, which is the initial guess for the unitary transformation. And if you want to do band interpolations, you need to also provide this eigenvalue file, which is written in the eigen file. So all the issue with the Wannierization is that this is a really high dimensional optimization problem. So it requires good initial guess from users, and you have to sometimes trial and error, like tune different parameters to reach a good set of Wannier function. So this is like sometimes especially for new users, this can be problematic. So algorithmically, the Wannierization can be classified into two cases. The first is this entangled bands. That is, there's no finite band gap to separate eigenvalues at each k point. So this can be like the metals. And the second case is these isolated bands. So like there's always a gap at each k point. So like the valence band of insulator. So we have to tackle these two cases differently. So for the valence plus conduction, we can construct this SMP like Wannier function. But for the valence or the conduction, they are the anti-bonding and bonding orbitals. So it's a little bit more difficult. So now let's focus to the first case. So that is the initial guess for the entangled bands. So now there are several existing methods for entangled bands. One of the standard ones is the hydrogenic orbitals projection. So this is what people often use in Wannier 90. Like when you write a projection block, you are essentially specifying the radial shape of these projectors. So here the projectors are spherical harmonics, that is a radial function of capital R, which depends only on the radial grid. And these spherical harmonics, which you can check their analytic form, these are the YLM, which only depends on these theta and phi of the coordinates. So these are the solutions of the hydrogenic Schrödinger equation. That's why we call it hydrogenic orbitals. And you can check from the table their radial shape, and you choose your initial projection based on your chemical intuition of your system. And in the projection block, you set like S, P, D, or even hybrid orbitals. Second, or like recent years, there's a second method called selected columns of the density matrix, which essentially does a QR decomposition of the real space density matrix. So this is a mathematical transformation, like you pass a density matrix here, and then you do a QR decomposition with column pivoting, and then you can select the columns to use them as the initial guess for your system. So this requires few user input from the user, but it can be automated, as we have seen in the Monday's tutorial for SCDM for the LED system. So recently we introduced this projectability disentangled Wannier function. So the name is a little bit long, but the idea is quite simple. So if we do a pseudopotential plane wave calculation like quantum espresso, there's actually a natural set of localized orbitals when we are generating the pseudopotential. So for instance, if we want to generate a pseudopotential like for silicon, we first need to do an isolated silicon atom Schrödinger equation. We solve this one-dimensional Schrödinger equation, and then we can get this O electron wave function, here the dashed line. So for instance, the 3s orbital, it has these two nodes, and the 3p, there's only one node. So the pseudization is actually removing the radial nodes. So we use some mathematical functions to make it continuous, and then we can remove this radial node, so we can use a lower energy cutoff. So these are already contained in the pseudopotential. Like for instance, if you want to compute a projected bands, these are the orbitals that's being used to get the projection coefficients. So in terms of these, we can use these orbitals to automate the initial projection of Wannier function. It has the additional benefit that they are adapted for each species. That means for different elements, you have different radial functions. So intrinsically, they are better than the hydrogenic radial function, which is just tailored for the hydrogen atom. Additionally, they also provide information on the semi-core states. So for instance, you have these deep energy states, and then these projectors, they already have different radial nodes, so they can already differentiate different projections. Like you cannot write 2S projection with the same radial function, radial nodes in your Wannier 90 projection block, then you can't get good Wannierization. But here, since they have the correct radial nodes, so they can directly give us good Wannierization for both semi-core and the valence electron, because most often you won't need the semi-core states. So in essence, we're trying to replace the analytic radial function by numerical radial functions. So we're replacing this hydrogenic R radial functions by this phi tilde. So this we can now compute it in PW to Wannier 90, and it will write the AMN file using these PAO projectors. Then the second ingredient is projectability disentanglement. So conventionally, we use these 4 parameters to specify the energy window for selecting states, and also the energy window for reproducing the DFT eigenvalue. So for instance, for the graphene band structure, we usually specify energy window here to reproduce good DFT eigenvalues around Fermi energy. So now we have a second criteria, we call it projectability disentanglement. The idea is simple. So if we look at this projected band structure of graphene, you see that these colored bands are the bands with high projectability. That means they can be represented by localized S and P orbitals. However, these states are not necessarily inside an energy window. So that's why we introduce this projectability window. So to select states that if the states has high projectability, that is, they are with colors, then we try to reproduce them in our Wannier function. If they have low projectability, like these gray bands, so these are the free electron-like bands. So naturally they are delocalized. So we don't need to include them. We shouldn't exclude them. So that's why we now have two thresholds to replace the aforementioned 4 parameters to keep the high projectability states and also to discard low projectability states. And the remaining state is just thrown in the disentanglement step. So this step is done in Wannier-90. So as a comparison, so on the left, I show the projectability of the band structure for graphene. Here, we try to use the standard way of hydrogenic projection with energy disentanglement. So we can reproduce nicely the frozen window, which is represented by this shaded area. But outside of this shaded area, we cannot guarantee that the bands are well reproduced. But for SCDM, actually, if you've done the tutorial, you know that the SCDM mu and sigma, the 2 remaining parameters, they are fitted according to the projectability of the system. So actually, when you're using SCDM, you're already using these localized orbitals. Well, for PDWF, we can nicely reproduce both the bands here and also the bands inside the conduction region. So this is only a single case. We further do a benchmark on 200 materials. So here we introduce a measure to estimate the band interpolation error. We call it band distance eta 2. So essentially, it's just the root mean squared error of the DFT eigenvalue with respect to the Wannier interpolated eigenvalue. So here we're using a window of Fermi energy +2. So we also compare the bottom of conduction band. So this is the histogram. So the PDWF Wannier function can interpolate better with a little bit higher accuracy, like on average, the error is like 4 millielectron-volt, which is already quite good. Well, for the SCDM, it's a little bit worse. So you see that it's around 11, and these interpolations, the beams of the histogram is not as well concentrated at around 0 as the PDWF case. In addition, we can also look at the spread of the Wannier function. So the PDWF is more localized here, while the SCDM, as I have shown you in the previous slides, in the graphene case, they can include those free electron-like bands in the density matrix. So usually you will get several Wannier function with large spread. And then we also use our algorithm and writing some automated AIDA workflows, which is just to automate the whole process of from SCF, NSCF, PW2 Wannier-90 to the final Wannier-90 calculation. So we can now fully automatically run Wannierization of 20,000 materials from materials called 3-dimensional crystal database. So we can, again, have quite accurate band interpolation error of around 3.6 millielectron-volt. So now let's switch to the second case, which is the initial gas for isolated bands. So as I mentioned before, the isolated bands is just the bands which has a finite gap with respect to others, like the valence band of insulators, but you can also do any isolated group of band, not necessarily just the valence band. So in this case, it's even harder to specify initial gas because you have to guess the shape of the bonding orbital and also the anti-bonding orbital, which are not simple SPDF orbitals anymore. So this relies even further on the chemical intuition of the people. Another use case is the Koopmans functional for improving the description of band gap. So in this algorithm, it requires 2 sets of projectors for the valence and the conduction band respectively. So that is also the reason why we're trying to solve the problem. So for this application, we introduced another algorithm called manifold remixed Wannier function. So here the difficulty is to, or the most severe problem is to Wannierize the conduction band, which involves both disentanglement and specifying a good set of initial projectors. So we tackle the problem instead in 2 steps. We first construct the PDWF, or if you want, any set of Wannier function which can well represent the valence plus conduction band as a whole. So we have, for instance, the S and P Wannier function for the valence and conduction band. And then we apply our MRWF algorithm to separate them into two groups. The first group is for the bonding, which is the valence band. And the second group is the anti-bonding. So why I'm saying this is anti-bonding, because if you look at here, the Wannier function, there's actually a noodle plane. So besides this noodle plane, the phase of the Wannier function, on one side is plus, and on the other side is minus. So it's really, they have this noodle structure, which is characteristic of these anti-bonding orbitals, where for bonding, they are localized at the bond center. So in practice, we are doing this like in 3 steps. The first is the Wannierization of valence plus conduction, and we separate the 2 submanifolds by diagonalizing the Hamiltonian. However, this diagonalization will break the gauge continuity, which is important for Wannier function. So essentially, we're returning back to the block gauge, but now we can understand which part are for the valence and which states are for the conduction just by grouping their eigenvalues. So now we have to fix this gauge discontinuity. So this can be achieved by using parallel transport and the combination of maximal localization. So I'll mention parallel transport later, but in the end, we will have a gauge matrix looking like this. So at each K point, or unitary matrices will have this block diagonal structure. The first part is for the valence, and the second part for conduction. So these are 2 fully orthogonal group of states. And meanwhile, they should be continuous across K points. So the key ingredient here is the parallel transport. So imagine like we have a set of DFT block states. Their gauge is continuous. They are sort of random. The parallel transport is like first running a singular value decomposition on the overlap matrices, so we can maximally overlap the gauge. It's like continuous now, but the issue is that our gauge should be quasi-periodic, or like, let's say periodic. So this shaded area should be the same as the first K point. So we have to find some method to move it back, and now it's both continuous and periodic. So there are some mathematical tricks to remove this so-called topological obstruction, but we won't go into detail further. It's just an algorithm which can fix the continuity of the system. So what are the results? So if we look at this MOS2 system, we first get this second column valence plus conduction band Wannier function, which are just the D and P orbitals. Once we apply our method, we have the valence band Wannier function, which are the bounding orbital. You see here, these Wannier functions summed like with the same coefficient, so they have the largest magnitude at the hexagon center. Well, for the conduction band, they are again the anti-bounding orbital, because you see that all these Wannier functions has a noodle plane, and the phase are different on the 2 sides. This happens for everything. And of course, we can reproduce nicely the Wannier bands for the valence Wannier function by these valence band Wannier function, and then the 4 conduction bands by these 4. So we can even do some strange Wannierization, like the top valence band of MOS2, and then you will have these quite interesting shape of Wannier function. Of course, it's a little bit more delocalized because we have only 1 band to do the maximal localization, so there's less freedom to localize the orbital. And if like some people are interested in this strontium vanadate, which is quite interesting material for DMFT people, so we can apply our method to single out the 3D manifold from all the remaining bands, and also you can separate the T2G and EG submanifolds from the 3D Wannier functions. And again, we do a little bit high throughput benchmark to validate the result is really working for various kind of chemical system. So we first do this valence plus conduction using our PDWF. And then we separate these into the valence band. You see these even more accurate, like less than 1 electron volt. Well, for conduction bands is, okay, the interpolation error is higher. So this can be explained by the localization of the orbital. As you can imagine the bonding orbital, they should be more localized. So indeed, these are more localized than the valence plus conduction band. Where for anti-bonding, they are delocalized, much delocalized than the valence band. So these will reduce the conduction band interpolation error, increase the conduction band interpolation error. So as a summary, I have remind us of how we construct maximum localized Wannier function from the DFT block wave function. So the key message is that we define a spread functional and we achieve smoothness of the gauge by minimizing this spread functional. And this minimization should be done on a unitary matrix manifold. And for the issue of the entangled bands, we introduce this projectability disentangled Wannier function. So these are optimal radial function, numerical radial function from the pseudopotential to replace the analytic hydrogenic orbitals. And then we can define a projectability window to single out the localized states. For the isolated band case, we introduce manifold remixed Wannier function. In the end, we're trying to get a gauge matrix that is block diagonal for the valence and conduction, and also they must be smooth. So this is done through parallel transport. So apart from these, there are like several other might be useful resources for daily usage of this Wannier 90 stuff. So first we have now this PW to Wannier 90 documentation on the Quantum Espresso website. So if you want to know further the meaning of this input tag, you can check out this website. And then we also recently converted the user guide.pdf into this website. So you can check out this website, and it should be like easy to search the meaning of the keyword, and also it's hopefully easier to write tutorials in the future. In addition, we also have, it's not released yet, but it will be online soon, Wannier 90 input generator. So it will automatically generate the SCF and SCF, all these input files with, or let's say SSSP pseudopotential, a set of verified pseudopotential. So these are all powered by the AIDA workflows we're using to do this high-throughput calculation. So because it's a static generator, so it loses some capability like error handling of the full AIDA workflow, but they should provide us a good starting point if you want to get just a quick input of your Wannier addition. So finally, I would like to acknowledge my supervisors, Professor Nicola Mazzari and Giovanni Pizzi, and also the funding agencies for their support, and also you for your attention.
Very much. So we have time for
Yeah, okay.
Well, can you please go back to slide 3, please? You said all of this requires a very good initial guess, but how do we have a good initial guess, make an indicated initial guess?
Okay. Thanks for the question. So yeah, so usually when people are doing this, it's like chemical intuition. Like you do like for silicon, you know it's S&P, and for some typical system, you also know like maybe you can choose sp3 like bonding orbitals. But the issue is here is that it indeed is not. It relies on human. So that's why we try to improve this by using the projectors, the orbitals from the pseudopotential file. In this case, you don't need to provide initial guess. So that is indeed what we're trying to solve.
Right. So sometimes the potentials may not be able to represent your reduction state or very entangled state. What would you do in that case?
Yeah, that's a very good question. So indeed, like for some set of pseudopotential, we don't have good enough localized states. And then if you apply this method, it might not work very well. But we have you can see in the second exercise. So for the let's say vanilla pseudopotential, they only have S and P for silicon, which if you want to really get accurate conduction bands, you need the d orbitals. So in this case, we implement a different way of using some radio function. Like you can generate radio functions yourself and pass it to PW to 190 to include the d orbitals. In this case, we regenerate the pseudopotential and get a set of localized 3D projectors. And in this case, if you include the 3D projectors, the conduction band will be better. But yeah, indeed, this is not as automated as using vanilla pseudopotential. So yeah, it's like a compromise. If you want to target a specific application, then you have to tune again something. But let's say for ordinary, or in our case, high throughput calculation, this for us is working. But for you, we can study in detail.
How do you define the projectability window? Is it like a frozen window or something, or it's different?
Yeah. Yeah, so we're not using energy window, but rather we try to freeze the states with high projectability. That is the states that can be represented by localized orbitals. So in this case, we're not using an energy window, but selecting the state, let's say from the color. So if they have a color, then we construct Wannier function from these states. Yeah, so you get rid of energy window. And this information is computed automatically, so you don't need to tune it. You can still tune it, but